Hello, this is Professor Jim Caffey, and today we are doing Chapter 15 on the Sun in our OpenStax Astronomy textbook. So let's get started. This is a picture from the SOHO spacecraft. It is a solar observatory in space aimed at the Sun. It takes continuous images. For comparison, we can put the Earth next to the Sun, and you can compare the sizes of the two. You note that a solar prominence over here is much bigger than the Earth. This woman helped define work among stars and the Sun, and she looked at the spectra of them to determine their chemical composition. This is the various parts of the Sun. On the inside we have a core where thermal nuclear fusion is going on. We have two energy zones, the radiative and convective zone. How they work are different to transport energy. In the atmosphere and surface we have the corona, a very hot atmosphere. Inside the chromosphere and photosphere, the visible surface of the Sun, and on that photosphere we have sunspots, dark areas that are cooler areas on the Sun. So how big is a sunspot? It is usually a lot bigger than the entire Earth. These sunspots have a granulation pattern to them. They look like boiling rice or soup. Here we see the Sun's atmosphere in different wavelengths, and you can see how active it gets when you look the right way. A coronagraph is a picture of the Sun that blocks out the Sun disk to get the outer atmosphere. And we see that here from SOHO. A coronal hole is a gap in the corona where solar wind and charged particles escape and go out into the solar wind and can interact with the Earth and cause these beautiful auroras, or northern and southern lights. This one was captured over Iceland. Sunspots usually appear in groups. They like to appear as twins, and the twins are polarized north-south magnetically, and they interact. These sunspots rotate with the Earth and the Sun with the Sun, not the Earth. And they take about 30 days to go across the solar disk. If we look at a sunspot and its magnetic properties, it will have an effect on spectral lines, looking at the chemicals, and the spectral line will split into two arcs right here on the right. And that is called the Zeeman effect, and it measures the amount of the magnetic field in the sunspots. This is a series of images of the Sun over the course of many years. And you can see it's active and not active over the course of an 11-year cycle. Well, there are magnetic field lines to the Sun, just like we have on Earth, except in the Sun, these lines get twisted up, and that helps form the sunspots. Prominences are large eruptions on the Sun. You saw a picture of the Earth earlier next to one. A solar flare comes from the sun, and we see one here in white coming out. These are hot, large explosions, very intense. We can have flares and coronal mass ejections, and we see those in these 4 images. Again, the solar pattern is about 11 years, and we can see here the sun being not active in 1996. It gets active by 2001, and then quiets down by 2006 again, and the cycle repeats. We can look at different wavelengths of the sun with our telescopes, and different wavelengths reveal different amounts of energy and interaction. One of the things that we do is monitor space weather. So space weather is how the sun and auroras interact with Earth and us. And NOAA's National Oceanic and Atmospheric Administration, the ones that bring you the National Weather Service, they are charged with predicting space weather. And you can see them inside there doing that. The number of sunspots also changes with the 11-year sunspot cycle. And here we see peaks about 10 or 11 years apart, where there's a bunch of sunspots, sometimes over 300, and then there are times where it's very quiet. Well, that's going to do it for chapter 15 on the sun. Thank you for joining me, and be sure to watch the next episode, chapter 16, coming up.